Hi everyone, my name is Taborno Barry from Barry Science Lab, and welcome back to Quantum Mechanics. Today, we'll be attempting to derive Bohr's equation in one lecture. So, this is a very difficult ordeal that leads directly from Schrodinger's equation in spherical coordinates. So, let's do a quick recap. What have we been doing for the past few lectures? Well, we started this whole series by considering the 1D Schrodinger equation. You probably know it pretty well by now. Mine is h bar squared over 2m I partial x psi is equal to I partial x t psi is equal to h bar squared over 2m partial x squared of psi minus u psi. This thing haunts our dreams at this point. But this is only the 1D Schrodinger equation, and we decided to take this into 3D by changing this to a Laplacian. But then we realized, or I said, that we have to use spherical coordinates. But why? Well, here's a quick consideration. Today, we'll be talking about the hydrogen atom. What is the hydrogen atom? Well, at its core, it's just one electron orbiting one proton at the center of the nucleus. Absolutely nothing intervening. Which means there's exactly one electromagnetic interaction we have to worry about. The gravitational force is negligible at this stage anyhow. By Coulomb's law, we know that the electric force between two charged particles is always equal to 1 over 4 pi epsilon naught r squared times the product of the magnitude, well, not the magnitude, the product of the two charges. Then that means that u, naturally, since Fe is the negative radial derivative of u, yes, it's technically not that simple most of the time, but when F is solely dependent on radius, the gradient acts this way. We get that u is equal to minus q1 q2 over 4 pi epsilon naught r squared. Should be, right? Yep. Oh, no. So now, consider that in a hydrogen atom, there's a proton with unit charge positive E and an electron with charge negative E. So the potential is going to be E squared over 4 pi epsilon naught r. Notice that the minuses cancel out. So here we go. This is the potential we're dealing with. Now, when we convert it to spherical coordinates, we painstakingly solved both the equation for theta, both the equation for theta and the equation for phi, up down to a few constants. But the problem with the radial equation is that just like the time-independent Schrodinger equation, it still depends on the potential function we want to choose. But this time, the equation is much worse. Now, you may recall that Schrodinger's equation in 1D, the time-independent Schrodinger equation, is minus h bar squared over 2m psi double prime, or psi x double prime, plus u psi x is equal to e psi x. Recall that from last time, the radial equation is instead the exact same thing. But with an extra term added onto it. Recall that this is the separation constant we used to break the triple variable partial differential equation, into 3 single variable equations. And here we go. This is the Schrodinger equation, or the Radial equation. Now, how do we approach this? Well, the first thing we want to do is condense this, because right now it looks really, really nasty. And when we actually plug in the potential function, things, as you can see, are only getting worse. First, let's divide everything by e. That gives us minus h bar squared over 2me psi r double prime plus e squared over 4 pi e epsilon naught e r psi r plus h bar squared over 2me L times L plus 1 over r squared psi r. And for the hell of it, let's just bring this psi r over here. Minus psi r is equal to 0. Now, that's not a minus, by the way. I don't know why it looks like that. Now, to condense it, we can't do much more than define a bunch of constants. So let's define the constants with very special names, because you'll see how they come into play later. Kappa being equal to the square root of minus 2me over h bar squared. As you'll see in a moment, and as you probably remember from high school physics, E is always negative for a hydrogen atom. Recall minus 13.6 electron volts. So this is always a real number. Then, well, this works here, this works there too, but we also have to deal with this. So what I'm going to do, personally, is I'm going to rewrite this as, let me pull out the notes. Recall that kappa squared is hence equal to minus 2me over h bar squared. So E is equal to h bar squared kappa squared over 2m. Don't forget the minus sign. And so what happens when we plug that into here? You get E squared over, well, this 4 becomes a 2 because it's canceling out with this guy over here. 2 pi h bar squared k kappa squared epsilon naught r, and there's going to be an m here, and this is all going to get surrounded by a negative sign. So I'm going to further factor this as minus me squared over 2 pi h bar squared kappa epsilon naught times 1 over kappa r. Now you might see a pattern. I'm trying to isolate a bunch of kappa r's here because I'm about to define a new variable. Rho is equal to kappa r. And what happens when we do that? Oh, and also, we're going to rename this nasty expression rho naught. So, just so you can keep track of what's happened so far, rho is currently equal to minus, well, currently it's not like it's going to change. It's equal to minus 2me over h bar squared, and rho naught is equal to, I actually don't remember, where I put its definition, me squared minus me squared over 2 pi epsilon naught h bar squared kappa. There we go. Oh, wait, no. So, what does this give us after all this time? Well, we've successfully condensed it into 1 over kappa squared psi r double prime plus, well, rather minus at this stage, minus rho naught divided by rho. 1 over kappa r is 1 over rho now. And what else is left here? plus h bar squared over 2m, which is minus 1 over kappa squared. Oh wait, this should have a psi r attached to it. Minus 1 over kappa squared, L times L plus 1 over r squared. And what else is there? Oh, right, just the minus 1, minus psi r. Now, you've probably been screaming at me the whole time to factor out the psi r. So let's do that. Here we go. So now, just to make sure, is that correct? Hey, wait a minute. We're not. Oh, yeah, that's correct. Okay. So, wait. Yeah, okay. So, this is now what we're left with. Or, well, yeah, this is basically our final form. And our first thought is, well, why not approach this with a power series? After all, got a bunch of nice decomposition right here. So what happens if we just try to plug in a power series? Let's assume psi r is equal to the sum from n equals 0 to infinity of a n rho to the n. So then, psi r double prime is, of course, the sum from n equals 0 to infinity of n times n minus 1 an rho to the n minus 2. And notice that the terms for n equals 0 and n equals 1 both go to 0. So now, what happens when you plug that in here? You get 1 over kappa squared multiplied by n equals 0 to infinity, n times n minus 1, an rho to the n minus 2. And that has to be subtracted from whatever this gives us, which is an rho naught rho to the n minus 1. And we already have to be cautious here because there's nothing else that depends on n other than an, which is oftentimes non-zero. Which means that this could give us a factor of 1 over rho, which can't be set to 0. So we'll just move onward and hope that that gets fixed sometime soon. And we get minus L times L plus 1 an rho naught, not rho naught, rho to the n minus 2, which is even more alarming because now we've introduced a degree minus 2 term. How do we cancel that out? And then plus 1 plus an rho to the n. That has to be equal to 0. But how do we do this? Let's try to analyze n equals 0 and n equals 1. Well, the term for n equals 0 is 1 over kappa squared. Well, actually, this doesn't exist for n equals 0. This disappears, and it also disappears for n equals 1, so we can ignore it. Which leaves us with this part, which gives us minus an rho naught, n equals 0, this is a naught. Rho to the n minus 1 becomes rho to the minus 1 for n equals 0. What do we do? Well, minus L times L plus 1, a naught p to the minus 2, rho to the minus 2, plus a naught, well, there is no rho to the 0. 0 is 1. That is the term for n equals 0. The term for n equals 1 is, well, everything over this way disappears, minus a1 rho naught, that this becomes 1 minus L times L plus 1, A1 rho to the minus 1, still there, plus A naught rho, which is n to the n equals 1. Now, you can see that this can cancel out this, so these two have to be equal. Well, they have to be, the negative of this has to be equal to this. This will get canceled out by the first term over here. This can get canceled out by this, so their coefficients have to be equal. But there's no other degree -2 term anywhere. If L is equal to 0, then we're going to get a trivial solution. And if L is not equal to 0, then the only way for this to give us a 0 power series is for A naught to be 0. But we know by these relations that A naught and A1 have to be proportional, which would make A1 0. And there's going to be a relation over this way when we create the next term that makes A1 proportional to A2, which means A2 must be 0. And so we'll get the trivial solution, psi r is equal to 0. Technically, that's a solution to the equation, but is it what happens in real life? So, psi r equals 0 implies that the entire wave function is 0. And a non-normalizable wave function means nothing. So, clearly, we've done something wrong. We have to get a better answer. But how? Well, our first thought is that maybe something went wrong because of the function's behavior at 0, which is where we centered the power series. How does the function behave at rho equals 0? After all, in spherical coordinates, the radius being equal to 0 and getting near that point is always pretty messy. So, how do we deal with this? Well, we look at the equation that we have right now. 1 over kappa squared times psi r double prime is equal to psi r multiplied by 1 plus rho naught over rho plus L times L plus 1 over rho squared. Now think about it for a moment. I guess to illustrate the point even more, nah, that's not necessary. So what happens here? Well, this term, out of all three of them, is going to dominate, as it's going to grow much faster as rho nears 0 than this term. And this term is constant, so it doesn't even grow at all. Which means that this approximately becomes 1 over kappa squared psi r double prime is equal to L times L plus 1 of psi r times 1 over rho squared. Now, as a reminder, rho is just kappa times r. So I can rewrite this as 1 over kappa squared r squared. Cancel these two out, and we get psi r double prime is equal to L times L plus 1 psi r 1 over r squared. And now it appears like psi r has to be a monomial of some sort. Think about it. When you take the derivative of a monomial twice, you're going to get some constant multiplied by it, and its degree is going to decrease by 2. The same thing that happens here. So we assume psi r is equal to r, or even better, a r to the k for some k. And now, solving for that k, we get psi r double prime is equal to a k minus 1 r to the k minus 2. And so a times k minus 1 r to the k minus 2 has to be equal to L times L plus 1 a r to the k minus 2. So you get to cancel these out, and looks like k times k minus 1 has to be equal to L times L plus 1. Now there are two solutions to this. Either k is equal to minus L, or k is equal to L plus 1. Now, which of these do we want to consider? Well, when you think about it, rho to the minus L is going to blow up as rho approaches 0. It's going to approach infinity, and something like this is one of the functions where, as it approaches infinity, its integral from 0 to any finite number is also going to diverge. And we don't want that because it breaks Born's statistical interpretation. So that is going to have to be out of the picture. This is not the solution we want. On the other hand, this, quite uniformly, as we approach 0, is going to also approach 0. Its behavior from 0 to 1 is going to be fairly well defined. So its integral is actually going to give us a positive value. And that is exactly what we want from a wave function, because it allows us to normalize it via Born's statistical interpretation. So there we go. That means that around 0, psi r is approximately near rho is equal to 0, rho to the L, the rho to the L plus 1. That's the solution that we picked. And so let's try to analyze its behavior near infinity as well. What does it approach then? Well, we get 1 over kappa squared psi r double prime. This is going to disappear as rho approaches infinity. So is that. The 1 is going to be the only thing that remains. Remember, this is an approximation as rho approaches infinity. Then, this is definitely just an exponential solution. So we pick the ansatz psi r is equal to a e to the k rho. Not necessarily the same k as before. And we get 1 over kappa squared k squared, e to the k r. 1 over kappa squared k squared e to the k r, multiplied by a, is equal to a e to the k r, which implies that k squared is equal to kappa squared, and so that k is equal to plus minus kappa. And kappa is always going to be a positive number, so now we have to contemplate what we're going to pick. Are we going to pick a e to the kappa r, or a e to the minus kappa r? Well, if we pick this one, its integral as we approach infinity is going to diverge. And that doesn't fit with Born's statistical interpretation. This is a non-normalizable wave function in that case. So we can't have that. The only other option is a e to the minus kappa r, which will diverge quite nicely. And you might say, well, what about its behavior when r is around 0, or when rho is around 0? Well, this is an approximation as psi r approaches infinity. When it approaches 0, psi r is going to look nothing like this. So think of it this way. Psi r is approximately near rho, or as rho approaches infinity. A, or e to the minus kappa r, or e to the minus kappa rho works too. So this is now what we're dealing with. And think of the function this way. A polynomial rho to the L plus 1 might look like this. So its integral as rho approaches infinity is going to diverge. And e to the minus kappa r might look like this. I can't actually remember. E to the minus kappa r. No, not that fast. Might look something like that. And both of their integrals diverge when you look at them over the entire real line. That's not the important part. The important part is that the function we are actually looking for, psi r, is going to act like this in the short term and act like this in the long term. And at the end of the day, its integral is going to stay finite. That's what we want. So, clearly, there's been an issue with expanding the power series over around zero for this function. But maybe we can try that again once we strip off all this asymptotic behavior. So what happens if we do that? Okay. All right. So what happens when we try to strip it of its asymptotic behavior? Let's introduce a new function, psi r overline, which is multiplied by e to the minus kappa rho and rho to the L plus 1. Once we've stripped it of the asymptotic behavior, well, now let's take the first and second derivatives. The first derivative is going to give us psi r prime is equal to, well, we have to use the product rule. Psi r overline prime times e to the minus kappa rho. Well, actually, no, it shouldn't be rho. Why did I say that? We said e to the minus kappa r. This should be minus rho. That's annoying. I'm not sure how I went that long without noticing that. Okay, oops. So we have psi r over line prime e to the minus rho to the L plus 1 plus the other term is going to be psi r over line times what happens when you take the derivative of this. Well, you get minus e to the minus rho to the L plus 1 plus L plus 1 e to the minus rho to the L. Now, looks like we can factor out e to the minus rho to the L plus 1, and that'll really help us condense this even more. So what happens when we do that? We get, well, maybe it's better to factor out e to the minus rho to the L, so we can prevent any 1 over rho terms from cropping up. E to the minus rho to the L, psi r overline prime rho, plus psi r overline, this is just going to become minus rho, so minus psi r overline rho, plus psi r overline, plus L plus 1 psi r overline. There we go. So that's the first derivative. It's not simple, but it's also not that bad. So I'm going to factorize this, factor out p over rho, so you get rho r over line prime minus rho r over psi r over line. So now what do we do with this? Well, we take the second derivative because that's the one that shows up in the equation. Kind of obvious, right? So we write psi r double prime is equal to, well, what happens when we take the derivative of this? That's why we factor out e to the minus rho. I don't want to do that. That's fine. We got e to the minus rho, rho to the L, minus e to the minus rho, rho to the L, plus L, rho to the L minus 1, e to the minus rho, multiplied by rho times psi r over line prime minus psi r over line plus L plus 1 psi r over line, plus the other term is what happens when we don't take the derivative, and we get we take the derivative of this part instead, which is more product rule, psi r over line prime minus psi r plus rho psi r over line double prime minus rho psi r over line prime. So that's that. Plus, you take the derivative of this, which is L plus 1 psi r over line prime. There we go. Okay. So now what happens when we factor out e to the minus rho, rho to the L again? We get e to the minus rho, rho to the L minus 1. Or let's factor out e to the minus rho, rho to the L minus 1 this time. We get minus rho plus L. So we get L minus rho in this container. Rho times psi r over line prime minus psi r over line plus L plus 1 psi r over line plus this gets factored out and just becomes rho, and on the inside you get the exact same thing. Now we look to simplify this even more because it still looks nasty. So we're going to try to group up all the terms in that inner bracket. So we get psi r prime prime is equal to e to the minus rho, rho to the L minus 1 times, so you get L minus L rho minus rho squared multiplied by psi r over line prime minus L rho minus rho squared psi r over line plus L minus rho times L plus 1, which becomes L squared minus L squared plus L minus L rho minus rho. Yeah, that sounds about right. Multiplied by psi r over line. And then you get plus this. Plus rho times psi r over line prime minus psi r, rho psi r over line plus rho squared psi r over line double prime minus rho squared psi r over line prime. And then plus rho L plus rho psi r over line prime. 4 lines. Wow. So now we group this up. First, we take the singular row psi r overline double prime term. Then we take all the psi r overline single prime terms, which become, well, you have this one first, rho L plus rho. Then you have this one second, minus rho squared. Then you have this one third, plus rho. Then you have that one fourth, plus rho, L rho minus rho squared. Is that right? No, it's cancel out, no? Or maybe, whatever. So, as you can see, this should give us 2 times this, which is nice. And we can factorize this even further to get, oh yeah, this is correct, 2 rho times L plus 1 minus rho. Good. So that's all of the psi r overline single prime terms factored. Then you have all the psi r overline terms, which became, well, you have the first term over here, which is minus L rho plus rho squared. Then you have that second term, holy hell, L squared plus L minus L rho minus rho. Then you have that third term, minus rho. Then that's it. So you get L squared minus 2L rho plus rho squared minus 2 rho plus L. Or L minus rho squared minus 2 rho plus L. So things are looking a little bit stressful, but we'll try to continue without issue. Now what can we do? Well, we substitute this back into the original equation and look for a solution through power series. So what's the equation that we get in the end? 1 over kappa squared e to the minus rho, rho to the L minus 1, rho squared psi r overline double prime plus 2 rho L plus 1 minus rho psi r overline single prime plus L minus rho squared plus 2L minus 2 rho plus L. Yeah, that's correct number of parentheses. Psi r overline. And this all has to be set equal to psi r multiplied by all of the other horrendous things. Psi r is just psi r is psi r overline multiplied by e to the minus rho multiplied by rho to the L plus 1, and that's surrounding 1 plus L times L plus 1 over rho squared plus rho naught over rho. And we can rewrite this as L minus 1 by bringing the rho squared into here and writing this as rho squared plus L squared plus L plus rho naught. Okay. So first, you may notice that we can cancel out these terms, which is a nice simplification. But now we are left with the spawn of, oh, wait a second, no, that's not. Hold up. So just as a quick aside, realize that psi r in that equation was still a function of r. Now psi r of rho functions a little differently because this is just kappa r, right? So when you take the derivative once, Well, this is basically just using the chain rule to give 1 over kappa psi r prime of r. You do it again, well, you get psi r double prime of kappa r is equal to 1 over kappa squared psi r double prime of r. And so, that gives us a good excuse to get rid of the 1 over kappa squared entirely, because we've now written it in terms of rho instead of a function of r. So that is going to disappear. And now we have a much cleaner situation all around. What else do we get? Well, now we try to bring all the psi r overline terms together. And we get psi r overline double prime multiplied by rho squared plus 2 rho times L plus 1 minus rho psi r overline single prime plus, well, actually, we're bringing all of this over to this side. So this is equal to psi r overline times L squared plus rho squared minus L squared minus rho squared plus 2L rho, oh no, minus 2 rho plus, plus 2 rho minus L plus L plus rho naught. So, these 4 folks disappear. Is that orange? No, it's red. What's this red? Oh, it's over here. Yeah, this one is slightly red-orange. And these guys disappear, which means that we're left with a stupidly simple expression. Now what do we get? Well, we have rho squared psi r overline double prime plus 2 rho L plus 1 minus rho psi r overline single prime is equal to psi r overline times 2L rho plus 2 rho plus rho naught. The power series solution is looking closer than ever. So now I'm going to take psi r overline double prime and substitute in the series, and let's use I this time because I'm feeling funky. The sum from I equals 0 to infinity of... No, it's empty anyway. Oh. Rho I. So, now what happens here? We take the second derivative and we get the sum from I equals 0 to infinity of, normally this would be rho to the I minus 2, but it gets multiplied by this to get normalized back to rho to the I. So you get AI times I minus 1 rho to the I plus whatever this is, this abomination, 2 times, how do I put this? 2L A to the I rho to the I, 2Li A to the I, AI rho to the I. Oh crap, I just realized I is the imaginary unit, and that's super prevalent. Everything we're doing right now is real. Sorry. So 2Li AI rho to the I. Yeah, that sounds correct. Plus 2 rho, which, so this is just 2I AI. Okay, thank you. 2I AI rho to the I minus 2i ai rho to the I plus 1. Yeah. So that's all of these terms. Now we have the term on the other side. Well, we're going to bring it back this way. So minus 2L rho to 2LAI rho to the I plus 1. And then plus 2 AI rho to the I plus 1. I'm just trying to be as careful as possible here. Plus rho naught AI to the rho to the I. What have I done? So now let's group things up. So that has to be equal to 0. Or in better terms, I'm going to write the mission statement on the whiteboard instead to give us more space to work on the blackboard. So we have to show that the sum from I equals 0 to infinity of the first behemoth is, let me look for the I plus 1 terms, minus 2i ai minus 2l ai plus 2ai rho to the I plus 1 plus rho naught ai plus ai I times I minus 1 plus 2li ai plus 2i ai times rho to the I has to be equal to 0. So as you can see, we've gotten ourselves in a sticky situation, folks. How do we get out of this? Well, hopefully you know power series, how to solve a differential equation using power series now, because I don't feel like covering it again. So, what's the I equals 0 term? Well, when I is equal to 0, you're going to get minus 2L A naught plus 2A naught rho plus what's going to be in this paren, rho naught A naught plus A, well, actually that's going to disappear, so we don't consider it. Plus, well, those two are also going to disappear, so we don't consider them. Plus rho naught A naught. What's I equals 1 going to be? Well, this term is going to be added. Still no news with this guy, but these two terms are going to be added. So we get minus 2 A1 minus 2L A1 plus 2A1 has to times rho squared. Yeah, that seems about right. Plus rho naught A1 plus, that's still going to disappear, 2L A1 plus 2A1 rho. Now consider that rho naught A naught has to be equal to 0. So something has to be up with this guy. Then, oh wait. So this can be a constant. But now consider that minus 2L A naught plus 2A naught has to be equal to minus 2 or minus rho naught A1 minus 2L A1 minus 2A1, since these two have to cancel out. So that gives us that A naught is equal to, well, actually, A naught times minus 2L plus 2 is equal to A1 times minus rho naught minus 2L minus 2. And so A1 is equal to minus rho naught minus 2L minus 2 over minus 2L plus 2. Or in Other words, rho naught plus 2L plus 2 over 2L minus 2 times A naught. So now, can we get this in general? Well, we get that A, n, for any n, well, actually we should probably pick I since that's the series index we've been going with, is going to give us what? Well, the kth term is going to be minus 2k ak minus 2l ak plus 2ak rho to the k plus 1 plus rho naught ak plus ak k minus 1 plus 2lk ak plus 2k ak rho to the k, and then I equals k plus 1 is just going to give us minus 2k plus 1 ak plus 1 minus 2l ak plus 1 plus 2ak plus 1 rho to the k plus 2. We actually ignore this term, so ignore, plus rho naught ak plus 1 plus ak plus 1 k plus 1 k plus 2l k plus 1 ak plus 1 plus 2k plus 1 ak plus 1 rho to the k plus 1. And we also ignore this. So in general, coefficient of this has to be equal to the negative of the coefficient of that. So 2k ak plus 2l ak minus 2ak, or in better terms, ak times minus 2k minus 2l plus 2, or 2k plus 2l minus 2, has to be equal to a rho naught plus k plus 1 times k plus 2l times k plus 1 plus 2 times k plus 1 a k plus 1. So in general, a k plus 1 is equal to 2k plus 2l minus 2 over rho naught plus k plus 1 times k plus 2l k plus 1 plus 2k plus 1 plus 2l plus 2 times k plus 1. And actually we can rewrite this as 2l plus 2 plus k times k plus 1 has to be equal, so ak plus 1 has to be equal to that times ak. So now we have to think, what happens for large values of k? Well, these two, L kind of shrinks into oblivion in comparison. No matter what value of L we choose, it's still finite and constant. So as k gets larger and larger, eventually it's going to outgrow L. So this is going to approximate 2 to the k, 2 times k divided by, well, rho naught is going to be gone with the wind. K plus 1, and these guys are going to be gone with the wind as well. K. There we go. And that's going to disappear further and leave us with 2k plus 1. For a large k, ak plus 1 is approximately 2 over k plus 1 ak. But think about the consequences of that. Then ak plus 1 is approximately 2 to the k over k plus 1 factorial. And so what happens when you sum? So remember, psi r overline is going to be the sum of ak multiplied by rho to the k, from k equals 0 to infinity. And so, what happens when you have 1/2 2 to the k divided by k factorial rho factorial? Well, this becomes rho to the k. Well, this becomes 2 rho to the k, and that is precisely 1/2 e to the 2 rho. But this blows up as rho approaches infinity, and it's exactly what we tried to avoid over there. So the only answer to this dilemma is that at some point the series must stop. And when it does stop, well, what are we left with? I have where do I go from here, actually? Oh, crap, I can't remember. Do you want me to look at it?
Yeah.
Okay. Oh, this isn't even mine. Yeah. Where's my notes?
Here, drink water.
Oh. Planned to use only one sheet of lecture notes, but clearly that was a mistake. Where is it? Oh, there. Oh, did I make a mistake? No, certainly not. Well. Let me see. Oh, there's what? Oh, yeah, that's correct. That's correct. So, okay. Oh, I must have made a sign error because my notes are saying that ak plus 1 is equal to 2k plus 2l minus 2 minus rho naught over 2l plus 2 plus k times k plus 1. Okay, well, let's continue with that in mind. So, let's say this is true. Then, at some point, 2k plus 2l minus 2 minus rho naught is equal to 0. Okay? But that doesn't make sense to me. After that, what should I do? Series must terminate. Yep. Oh, beyond this. Yep, I'm dumb. So, recall that since, an is proportional to a minus 1, n minus 1, it's just an minus 1 times some constant that depends on n. Then, if an is equal to 0, that means that an plus 1 is equal to 0, an plus 2 is equal to 0, n plus 3, so on and so forth. If one element is 0, then the entire series is just finite. Everything else gets cut off. Which gives us that there's some k such that this is true. And after that, it has to vanish because otherwise, as I said, well, this is going to spiral off into chaos. So one more thing, I'm not certain why I got the rho naught here instead of here. But anyhow, it doesn't really matter at this point. So what k is this possible for? Well, it has to be rho naught plus 2l, rho naught minus 2l plus 2 over 2. And after that, everything else has to die, unfortunately. So there we go. This is the final term in the series that's going to define psi r. But what does this tell us? Crap, I actually forgot what this tells me. In that case. Oh, right. Okay. Never mind. Sorry. So, recall that since a long time ago we said, where is it now? Rho naught is this. So rho naught is equal to me squared divided by 2 pi epsilon naught h bar squared, and kappa. Recall that, this should be, this should have r, but forget it. Kappa, well, 1 over kappa is going to give us h bar, so minus h bar divided by 2, the square root of 2me. So this is going to disappear. And rho naught is this. Look at that. There's a little guy in there, 2me. So what I'm going to do is abbreviate this whole mess as c times 1 over the square root of e. Now what do we get? Well, c over the square root of e is equal to 2k plus 2l minus 2. And so the square root of e over c is equal to 1 over 2k plus 2l minus 2. And the final straw is e is equal to c squared over 2k plus 2l minus 2 squared. And now recall that k is the series index. So at the end of the day, this is what? It's c squared over a bunch of constants plus there's going to be a term in there that's minus 4k. There's going to be a term in there that's plus 4lk. But the most important term in there is plus 4k squared. Now, to rewrite it in more familiar notation, I probably should have used n. But the allowed energies are c squared over c1 minus 4n plus 4ln plus 4n squared. And for large n, these terms disappear. And what does this become? C squared over 4 times 1 over n squared. That's right. After all this time, this reduces to an inverse quadratic. The allowed energies all take this form. Now, if you really want to, this also tells you the form of psi r by itself, but that's not the important part anymore. The important part is that we have Bohr's equation, and it's crazy, but it works. That's it for today.
Bohr himself did it.
Yes. That's it. Thank you everyone for watching, and we'll see you in the next one.
He must have very smart.
And he didn't have a textbook to help him.
Oh no, he did it very good. Everything from scratch, I guess.